Hello students, hope that you are all doing well in this difficult situation with a request to stay at your home, to not roam in the street. I shall start today's discussion on relation. It's a part of your discrete mathematics gate syllabus. In today's lecture, we shall learn what is relation, what about some different type of relations and the examples. In this short video lecture, we shall also try to solve a couple of MCQ from GATE papers. So we shall learn what is relation now. You consider two set A and B. In that case, any subset of A cross B is a relation. As for example, suppose that you take capital A equal to 1 to capital B equal to A B. You will note that then A cross B is the Cartesian product of A and B. Any subset of A cross B can be R. So R equal to suppose 1 comma A and 2 comma A and 1 comma B. Then capital R is a subset of A cross B. Therefore, capital R is the relation on A cross B. However, in your syllabus, we shall mainly focus on binary relation. What is a binary relation? A binary relation is a subset of A cross A. That means in particular, if you take B equal to A, you get A cross A as the Cartesian product of A with A, and any subset of A cross A, say it is R. R is a binary relation on capital A. Now we shall learn what about equivalence relation. You may note that there are different types of relations. As for example, some relations can be reflexive, some relation can be irreflexive, some relation can be symmetric, some relation can be asymmetric, some relation can be anti-symmetric, some relation can be transitive. Among these different relations, you combine reflexive, symmetric, and transitive. If a relation is reflexive, symmetric, as well as transitive, we say that the relation is an equivalence relation. So mainly we shall focus on equivalence relation or in these three definitions in today's discussion. So what is a reflexive relation? A relation capital R on a set A is reflexive if, so capital R is a subset of A cross A, and capital R is reflexive if for all elements in capital A comma A are in R. Consider an example. Suppose that you consider capital A to be the set 1, 2, 3. In that case, suppose capital R you take, it is 1, 1, 1, 2, 2, 2, 3, 1, and 3, 3. We shall check whether this relation is reflexive or not. To do that, you can construct the relation matrix. How do you do that? Suppose you put all the elements of capital A along the row and also along the column so that you can construct a matrix like this. Now, what about the how many elements are there in the matrix? This matrix is a 3 cross 3 matrix. It shall contain 9 elements. What about the first position? This position is 1, 1 position. You check whether the element 1, 1 is in the set or not. You find that yes, 1, 1 is in R. So you mark it with unity. Next, what is the position? This position is 1, 2 position. You also check that 1, 2 is in R. So you also mark it with unity. Next, you move to 1, 3 position. But you may note that among the remaining elements, 1, 3 is not present. Therefore, what you should do? You should mark it with 0. Similarly, in the second row, 2, 1 is absent, it's 0. 2, 2 is present, it's 1. Look, 2, 2 is there. 2, 3 is absent, you put 0. 3, 1 is present, so you put 1 over there. 3, 2 is absent, mark it with 0. 3 is present, mark it with 1. And this is the relation matrix of R on the set capital A. Now, you may note that in this relation matrix, what about the principal diagonal? You find that along the principal diagonal, all the entries are unity. And this is one condition that will show you that the relation is reflexive. Means, in a reflexive relation, in the relation matrix, all the elements along the principal diagonal are necessarily unity. There is another property to check whether the relation is reflexive or not. You can use diagram over that, but we shall discuss it when you learn what is graph theory. Okay, so you find what is reflexive relation. Now, along with that, we can also note what is an irreflexive relation. What is irreflexive relation? It states that for all elements in capital A comma A cannot be in capital R. This means even if for every element A in capital A, your A comma A in no case can be in capital R. As for example, suppose that you take capital A equal to 1, 2, 3 as we did earlier, and suppose capital R equal to 1, 2 and 2, 3. That much only. Okay, we shall check whether this relation is irreflexive or not. To do that, you can construct the relation matrix like this: 1, 2, 3 row wise, 1, 2, 3 column wise, to get the 3 by 3 matrix. Since capital A contains 3 elements, so the matrix will also be of size 3 by 3. 1, 1 is not present in capital R, you put 0. Look, 1, 2 is there, so you put 1 over there. 2, 3 is over there, to 2 put 1 over there. But for the rest elements, you put 0. So there is 0, you put 0 over there, you put 0, you put 0 at this place, you put 0 at 3, 2 place, you put 0 at 3, 3 place as well. In this case, you note that all the elements along the principal diagonal are necessarily 0. And therefore, this relation is an irreflexive relation. So if you find that all the elements along the principal diagonal are necessarily 0, then the relation is an irreflexive relation. Okay. Next, we shall learn what is symmetric relation. To learn symmetric relation, you note for all A comma B belongs to the set capital A comma B belongs to R implies B comma A belongs to R. Therefore, this shows that the relation is a symmetric relation. Consider an example. Suppose that you take capital A to B 1, 2, 3 as we did earlier. In this case, capital R you can choose arbitrarily any subset of A cross A, and you shall check whether that subset is symmetric or not. In this case, you can take capital R equal to 1, 1, 1, 3, 2, 3, 3, 1. Now construct the relation matrix. To do that, you again place 1, 2, 3 horizontally, 1, 2, 3 vertically, and that is the table that you have. Look, 1, 1 is there, so we mark it with unity. 1, 3 is there, mark it with unity in the table. 2, 3 is there, you mark it with unity. 3, 1 is present, so mark it with unity. What about the rest elements? In the rest place, since the elements are not present in capital R, you mark them with 0 as we did earlier. So you have the relation matrix like this. First, check whether this matrix is a symmetric matrix or not. What is a symmetric matrix? Symmetric matrix means the principal diagonal works as the mirror image. So what is the principal diagonal over there? You may note that in this case, this is the principal diagonal, and if it is the mirror, in this implies that if it works like a mirror, in that case, check. Look, this is 0 at 1, 2 place, 2, 1, it is also 0. 1, 3, it's unity. So its mirror image is at 3, 1 position, it's unity. 2, 3, the position is 1, gives you 1. But what about the mirror image of 2, 3? It is 3, 2. You check that no, it is not 1, but it is 0. So this principal diagonal cannot work like a mirror in this case. That means the matrix cannot be a symmetric matrix. If the matrix is not symmetric, the relation cannot be a symmetric relation. Okay. Next, we shall learn what is transitive relation. To do that, you take any a comma b comma c in capital A and you check if a comma b belongs to R and b comma c belongs to R, this should imply that a comma c belongs to R. We shall check with an example this time again. You take capital A equal to 1, 2, 3 as we did earlier, and capital R equal to, you take 1, 1, 1, 3, 2, 2, 2, 3, 3, 1, my arbitrary choice. We shall check whether this relation capital R is transitive on capital A. For that, you construct the table 1, 2, 3, 1, 2, 3, and you check that in this case, this first position is 1, 1. It is in the relation R, so you mark it with unity. What about the next position? It's 1, 2. Look, no 1, 2 is there in the relation R, so mark it with 0. What about 1, 3? Yes, 1, 3 is there, so mark it with unity. What about 2, 1? No, 2, 2, 2, 1 is not there, so mark it with 0. As before, 2, 2 can be found, so 2, 2 you put, oh sorry, it's not 0, but 2, 2 you put 1. 2, 3 you again put 1 because it is there. 3, 1 is 1, 3, 2 is 0, and 3, 3 is again 0. So this is the relation matrix that you have, and you have to check whether the relation is transitive or not. How do you check? You check that in this case, 1, 1 is there, 1, 3 is there, so 1, 3 is also there. 1, 1, it acts like A, it is B, and it is B, it is C. If you combine this, A comma B belongs to R, B comma C belongs to R, then A comma C, which is again 1, 3, it belongs to R. So there is no point in checking this combination or this type of combinations. But what you can do, you can check that 1, 3 is there, 3, 1 is there. So 1, 3 is there, 3, 1 is there, AB is there, BC is there, and what about AC? In this case, if it is AB and this is BC, AC is clearly 1, 1. So you find, yes, 1, 1 is in capital R, isn't it? Next, this shows that this relation is transitive. Remember, you have to do the checking for every position, for every pair, for every ordered pair in capital R. This will show that the matrix is the relation is a transitive relation. Therefore, if a relation is reflexive, symmetric, and transitive, it is called equivalence relation. There are many properties of equivalence relation. We shall learn it through MCQ. Here we consider one question from year 2015, say 2. It states that capital R is a relation on the set of all positive integers such that A comma B belongs to R if biconditional if and only if A comma B are distinct and have common divisor other than 1. That means they are not relatively prime to one another. So let us learn what is the given set. The given set is the set of all positive integers. And what about the relation? The relation is that A comma B is in the relation if they are distinct and they have a common divisor other than 1. That means there is they are not relatively prime, in other words. So what is the question? Now there are 4 choices. The relation is symmetric and reflexive but not transitive is the first choice. Repeating, the relation is symmetric and reflexive but not transitive. Choice B. R is reflexive but not symmetric, not transitive. Choice C. R is transitive but not reflexive, not symmetric. Choice D. R is symmetric but not reflexive, not transitive. This means that we shall learn whether we shall have to do whether this relation capital R is reflexive, symmetric, or transitive. That checking we need to perform. Yes or no? Think about it. You can, if you can establish a counter example showing that this relation R is not equivalence, then it is fine. Check. You find that in this case, you can take 3,6 in capital R. Yes or no? Because both 3 and 6, they are distinct, and the common divisor of 3 and 6 is 2, which is more than 1. Therefore, you find that 3,6 can be in R. What about other pair? You can take 6,10. 6,10 is also in R because 6 and 10 are distinct, and the common divisor of 6 and 10 is 2, which is more than 1. So 6,10 is also in R. However, you note that if you consider for transitivity, A comma B belongs to R, B comma C belongs to R, but what about A comma C? If you take A comma C in this scenario, it is 3,10. It cannot be in R. Why? Clearly, 3 and 10 are relatively prime to one another. The common divisor of 3 and 10 is 1. It shows that 3, 10 cannot be in R, so the relation cannot be transitive. Is the relation reflexive? I hope you have already determined that much. The relation is not reflexive as well, because suppose you take any positive integer A comma A cannot be in R, because it is given that A comma B belongs to R when they are distinct. So the relation is not reflexive, is neither reflexive nor transitive. What if the symmetricity? You may note that if you take any A comma B belongs to R, this means that A and B are distinct and the common divisor is more than 1. Clearly, if you take the reverse pair B comma A, then B and A are also distinct since A comma B are distinct. And since A comma B has divisor more than 1, B and A will also have a common divisor more than 1. So B comma A has to be in R. Therefore, the relation is symmetric. This shows that the relation is symmetric but not reflexive nor transitive. Hope that this cleared your doubts. You can consider another example, and this time from GATE 2010, a little bit old GATE paper. However, we can consider it because this involves a formula. What is the possible number of reflexive relation on a set of 5 elements? So a set, suppose capital A, it contains 5 elements. What about the number of reflexive relation on this set? You may note that if a set contains n elements, the number of reflexive relation on it is 2 power n square minus n. Got it? What is n? N is the number of elements in the set. Therefore, in this case, if you put n equal to 5, 2 power n square minus n is 25 minus 20 is 2 power 20. What are the given choices? The choices are 2 power 10, 2 power 15, 2 power 20, 2 power 25. So what is the correct choice? Clearly, choice C, 2 power 20 is the correct choice without ambiguity by using this simple formula. We shall learn a lot of tricks like that when you learn the relation in detail. Thank you very much for listening.